It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is for differential equations students who are going through exact equations. They've actually just learned, or you should have just learned, about what an exact equation is, and you might have already learned how to force exactness with an equation, but that's not what we're going to do here. We're just going to see if an equation is exact, and if it is, we're going to go ahead and solve that differential equation. Now, before I get too far into this video, I do want to apologize if you hear some bouncing on my microphone. I just purchased a new microphone and I don't have the shock mount as of yet. So again, if you hear a little bit of a bounce or some harsh low ends coming through, it's because of that. Anyhow, so something I do want to mention here, when you go in to see if an equation, a differential equation, is exact, my notation for doing this is slightly different than most textbooks. So I'm going to start with that. First thing I'm going to do here is separate the variables. Maybe that's the incorrect phrasing. I'm going to rewrite this in what I call differential form. All right, now that we are in differential form, that is, it's no longer written as dy dt, but instead in terms of differentials, we're going to go ahead and see if this is exact. Now remember, an equation, a differential equation, is exact if you can find a function, or if there exists a function such that the partial of that function with respect to y is the coefficient of the differential of y, and the partial of that function with respect to t is the coefficient of the differential dt. Now, we cannot guarantee that such a function exists just at the beginning of a problem. We can't just look at this and say, yep, that function exists. We totally know a function exists such that f sub y is this business in front of dy, and f sub t is this business in front of dt. However, there is a way to determine if such a function exists. It's a little bit of work, but not too much. Before we dip into it, I'm going to use a different notation here. Because I cannot guarantee that the coefficient of the differential of y is f sub y, and because I cannot guarantee that the coefficient of the differential of t is f sub t, I'm going to call those coefficients something different. In fact, I use that notation there. So because we cannot assume the coefficients of dy and dt are f sub y and f sub t respectively, we will instead just create function names, capital Y and capital T. Capital Y is a function of both t, little t, and little y, and capital T is a function of both little t and little y. And again, our goal is to showcase that there is such a function, that f sub y is equal to that capital Y, and that f sub t is equal to that capital T. But the only way to guarantee that such a function exists is if the partial of capital Y with respect to t is the same as the partial of capital T with respect to y. This is true if and only if there is a function, capital F, whose partial with respect to y is capital Y, and whose partial with respect to t is capital T. That is, if this is true, we have that situation right there. And in fact, this is an if and only if. So it goes both ways. It's a bijection. And usually this theorem is actually from Calc 3, multivariable calculus, and we don't really prove it in differential equations. So let's go ahead and tackle this here, and then we're going to come back and loop around in this problem and talk about an alternative tactic that you might consider trying, but really won't work out. So let's go ahead and try this here. Taking a look at y sub t. First of all, capital Y, the function, I'm going to rewrite that a little bit because honestly, I just don't like the way it looks. I personally like to work with negative exponents. It's pretty easy in calculus to do that, so I like this. Now let's take the partial of y, again with respect to t. And we arrive at that guy right there. Now we hope that's going to be the same as the partial of t with respect to y. And I am going to go ahead and just rewrite the function t, or the coefficient function t, in terms of negative exponents as well. All right, I think I did that okay. Let's take the partial of t with respect to y. So let's see what we have right now. The partial of t with respect to y is negative 2t, y to the negative fifth. And let's see, the partial of y with respect to t is negative 2t, y to the negative fifth, the same thing. So we're very lucky. This equation that we originally handed, that differential equation right there, and in fact, it is technically an IVP, but we'll deal with that in a moment. It is an exact equation, which means there's a really interesting way to solve it, because we happen to know the coefficient of dy is now, we can now guarantee there is a function f whose partial with respect to y is that coefficient of dy, and that for that same function, capital F, its partial with respect to t is the coefficient of dt. Now, here's the cool thing about this, and my students have already seen this in class, but if you're not my student, you probably haven't seen this. Because you have two functions, well, you have one function, but two of its derivatives, its partials, it's like you're climbing two different ladders. So if you've taken Calc 1 with me, or if you've seen my Calc 1 videos, you know that I think of calculus and differentiation and integration as a ladder. Now, what the heck do I mean that I think of integration and differentiation as kind of being on a ladder in mathematics? Well, back in Calc 1, when you learn to differentiate a function, I always would tell my students, you're standing on a rung and you have some function. Let's just call that function little f. And when you take its derivative, you tend to, but not always, but you tend to lose information. Think about a polynomial. When you take the derivative of a polynomial, there's a chance that you lose a term during that differentiation. So when you take derivatives, you are losing information. The ladder of information that you have gets narrower and narrower. So you get less and less information the more derivatives you have. If you have a third degree polynomial, for example, and you take 4 derivatives, well, you have hardly any information left for that polynomial. Likewise, when you take integrals or antiderivatives, you climb this ladder. And when you climb the ladder, it gets wider, and that's because every time that you find an antiderivative, you're adding a constant of integration, and that gives you more information. By the way, the traditional notation for an antiderivative is the capital letter, which is going to be somewhat confounding in a differential equations course. But that's what I mean by differential calculus or derivatives and integrals being kind of a ladder perspective. Well, that's going to help us here. I'm going to go ahead and erase all this stuff right here. I'll keep the rungs in there. Not that I have to keep all of them. In fact, maybe I'll just keep the bottom and the top one for right now. And what I'm going to do is list out what we have said f sub y is and what we said f sub t is. And I'll have a ladder related to y and related to t. All right, so we know that f sub y is 3y squared minus t squared over y to the fifth. Well, a better way to write that is 3y to the negative third minus t squared y to the negative fifth. So let me write that down. All right, and on the other ladder, I'm going to write what f sub t is. That is the partial of f with respect to t. When I say f sub t, please forgive me. It's a habit that I have. It's the partial of f with respect to t. So let me go ahead and write that down. All right, we have everything set up. Now what I'm going to do is choose one of those ladders to climb up. In other words, I'm going to integrate one of those functions with respect to the partial that we have taken. So in other words, if I chose to climb this leftmost ladder, I would integrate with respect to y, holding t as a constant. Likewise, if I chose to climb this rightmost ladder, I would integrate with respect to t, holding y constant. Now, if you take a look at this, make a smart choice, right? Which of these two would you like to integrate? I'd like to integrate the one that looks less complicated. So I'm going to integrate the one on the right-hand side. So let's go ahead and climb this ladder by integrating with respect to t. Now again, y is going to be considered as a constant here, and that's going to be very important. Now let's go ahead and integrate this. Now, normally, when you evaluate an indefinite integral, you get a constant of integration that pops out. Normally, that constant is an arbitrary constant, and we think of them like pi or e or -2 or something like that. But because we held y constant in this process of integration, it could be that our constant of integration is actually some function of y. And so I'm going to write that in here. Again, because we integrated with respect to t and held y as a constant, our constant of integration is likely going to be a function of y. Not necessarily, but likely. So I've climbed this ladder. I found out this right here is what f of t comma y is. So that should be the same as f on this ladder. So what we're going to do is, since we climb this ladder to find f, and then we transposed it over here, we're going to go ahead and take the derivative, the partial of this function f with respect to y to make sure that these two are equal, and they won't be. But this is a very important step. So here I go. I'm going to go ahead and take the partial of f with respect to y using this new function we just found. And watch what happens. We get a -t² y to the -5th, plus, again, we're taking the partial with respect to y, so we're taking the derivative with respect to y. So plus a g prime of y. Now, if you compare this version of f of y that we just arrived at with this version of f sub y, and I keep saying f sub y, I mean the partial of f with respect to y, pardon me, you'll see that they're very similar. In fact, you can see that this piece right here matches that piece identically. However, this does not match that identically, but those two things must be equal. That is, g prime must equal 3y to the -3rd. And now I can find g by integrating both sides of this with respect to y. Remember, if you take a look up above, we happen to know what f of ty is. It is 1/4 t² y to the -4th plus some unknown function g of y. We need to find that function. So integrating this with respect to y allows us to do that. Now, when you integrate, you get that constant of integration, right? And it turns out when you're solving exact differential equations, your solutions will be implicitly defined curves. In other words, your solutions will always be of the form f of, in this case, t comma y is equal to some constant c. And I personally like to say it's equal to 0, only because when I go through the process the way that I do it, this constant of integration right there is actually going to be moved over to this side eventually. Let's see how this works. So up above, and I'll highlight in blue right here, this piece is actually what f of t comma y is. So let's go ahead and plug that in to our implicit solution right here. And remember, we had a plus g of y. We've just found out what g of y is. It's a -3/2 y to the -2 plus c, and that is equal to 0. Now, you move that c to the other side, and to be very honest with you, it's just a constant of integration. This is going to be somewhat abusive with my notation. In fact, maybe I should do this. I'll call that c sub 1. So this is c sub 1. When I subtract c sub 1 from both sides of this equation, I get negative c sub 1 on the other side, but that's just another constant. So I just call that c at that point. Now, the last thing we need to do before I'm going to rewind the tape here and talk about some other tactic that you somewhat might be attracted to doing, we need to worry about the IVP. So let's go ahead and worry about this initial condition. Usually with IVPs, they only differ from regular differential equations in that you have one final little step, some little bit of algebra at the very end. So I happen to know when t is 1, y is 1. So let's go ahead and substitute those in to find out what c is. IC means initial condition. I'm just substituting those in. So we get that C is -5/4. And let's go ahead and just rewrite the implicit solution one final time. This time, I just, for giggles, I'm going to go ahead and write it with positive exponents. You don't have to be very honest with you, but I'm choosing to. Again, you don't have to write that with positive exponents. You could have used negative exponents. And you could also multiply both sides by 4 if you wanted to. It doesn't really matter. But that is the solution to the IVP. Now, before I leave this video, I want to, because all this video is going to be is just a single example, I want to just turn your attention to a tactic that some people might want to try because it is super attractive. So one thing a lot of people might want to do is they might want to multiply both sides of this differential equation by 2y to the 5th. Because people don't like fractions. It's just how it is. Myself included. I'm not a huge fan. So if we did that, what would happen? Let's pretend we want to go ahead and grab that differential equation and start by multiplying both sides by 2y to the 5th, which is the LCD. There is a slight danger from the get-go by doing this. The first big kind of dangerous piece is that you lose part of your singularities, right? You have a singular point, or you have issues, I should say, when y is 0. So when you multiply both sides by the LCD, you're kind of removing from your vision the fact that you don't have solutions at y when y is 0. So that's a concern. But another issue that creeps up here is that this might not be exact anymore. And this is kind of the neat thing about exact equations is sometimes, well, when written one way, they're exact. However, when you manipulate them, they might not be. So let's see if this is exact. Remember, I cannot assume that that coefficient of dy is the partial of f with respect to y, and I cannot assume that the coefficient of dt is the partial of f with respect to t. What I need to do is see if the partial of this capital Y with respect to t is the same as the partial of capital T with respect to y. If that's true, then I happen to know there is a function f such that the partial of f with respect to y is that coefficient of dy, and the partial of f with respect to t is the coefficient of dt. However, when you do this, you see immediately that y sub t is not equal to t sub y. So this equation is not exact. And that's a massive issue, right? Once you do not have an exact equation, then you don't have a function whose partial with respect to y is that coefficient of dy and whose partial with respect to t is that coefficient of dt. So you can't do this whole build a ladder concept, climb one ladder, hop over the next, and climb down and compare constants of integration. There's just no way to do that. So be very, very careful. If you want to clean things up at the beginning with a given differential equation that you think might be exact, it's okay to try, but I actually would probably just go ahead and deal with the form you were given to see if it's exact. Anyhow, I hope that this video helps you out in your journey through differential equations. Have a great day. Be a wonderful human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.